Okay, so welcome to Math 349, Operations of Order. This is lecture 3. And so what I want to do for the first week or two of this class, do you have anything you can wear over that?
My jacket.
If you could put on your jacket, that would be appreciated, especially after last night.
Yeah.
So what I want to do for the first week or two is give you a sense of possible topics and things to explore. And so we talked a little bit about Fibonacci numbers in the last lecture. We'll talk much more about Fibonacci's later. I want to talk a little bit more on the analysis side. Out of curiosity, how many of you have taken real analysis? Okay, so not that many. So this is actually somewhat good in that you haven't seen which things can be justified or not for many of you. And so it'll be an interesting way to look at this. So one of the biggest difficulties in mathematics is always, when is something justified? So frequently you can put on additional conditions, and the more conditions you put on, the more likely it is that you will have a result that is true. But of course, then the less useful the result is going to be in general. When I was a student, I always wanted results proved in as great generality as possible. And I was always upset when simplifying assumptions were made. When I became a professional mathematician, well, of course my function is infinitely differentiable and its Taylor series converges to it. Why would I ever look at any function where this is not true? And so it's, what are you using stuff for? And so what I want to talk about right now is just some results from integration, and just give you a little bit of a sense of how do you find what the right conditions are for the results that you want to be true, as well as what might actually be true and what might not be. And so the goal is to eventually get to some situations where you talk about interchanging orders. And the interchange will sometimes be justified, sometimes it will not. So here's an interesting question that I will start with. Say the integral from minus infinity to infinity of f of x, g of x, dx equals 0 for all g of x. What is true about f of x? Any thoughts about what might be true? Can you think of any functions that might satisfy this? Yeah, always default be the smartass. Well, what if I just take the function that's identical to 0? So we know f of x equals 0 works. Any conjectures? Can you think of any other functions that might work? So f of x equals 1 everywhere? It can be fixed. So does anybody know how to add vertical lines to the word assume? Yep. When you assume, you make an ass out of you and me. And I'm not using profanity. I'm talking about a small animal that can haul massive amounts of supplies. What are you assuming about f? Why? Where did I say that? Where did I say that f is continuous? Function does not have to be continuous to be integrable. So all I've assumed is by writing down the integral, I have implicitly assumed f is integrable, but that does not mean it has to be continuous. So I've got something that's at least Riemann integrable. So when you're looking at problems, it's very easy to just accidentally assume more than is stated. I have just stated that the integral of f of x g of x equals 0. So if the function doesn't have to be continuous, it at least has to be integrable. Can anybody give me another function other than f of x equals 0 that works? Any other thoughts? So if you take 1 over x, that means no matter what g I take, the integral has to be 0. Okay, so if you take f of x as, you said 1?
Yeah, on the negative side.
Okay, but then if I just take g of x to be, say, 1 from -3 to -2, then the integral won't be 0. This has to be true for any g of x that I take. There's one natural g of x that you can take that's going to cause some trouble. What would be a good g of x to look at to cause trouble? Yeah, this integral has to be 0. You try to think, what would be an interesting g of x to take? There's only one other function in play. What's the one function in play? F of x. So, somehow got light. So, if g of x equals f of x, we have the integral from -infinity to infinity of f of x squared dx equals 0. What must be true now? So I give you a function. So I'll add something. Let's assume f is real valued. If not, do g of x equals f of x bar below. So you could easily modify this argument to hold if f is complex valued by just taking g of x to be the complex conjugate of f. I'm now giving you a function and I square it and its integral is 0. What must be true about the function? Does it have to be the 0 function? Can you give me any function that's not identically 0, such that when I square it? So what kind of values can f of x squared be? And so can f of x squared be negative? No. So it could be positive. What else could it be? 0. So f of x squared is non-negative. But I want this integral to be 0. Is that enough to force f of x squared to be 0 everywhere? We're not assuming f is continuous, right? I'm just giving you, I have some function, the integral of its square is 0. Can you give me a function whose integral of its square is 0, but the function is not identically 0? Well, if you take x or x squared, that's going to be non-zero in regions of space, right? So if you take, say, x squared, that's clearly going to be non-zero from 1 to 2. When I square it, it's going to be positive from 1 to 2. So this integral won't be 0. So if I, you're still thinking of a continuous function. You have to give me almost surely something that's not continuous. What's the simplest function you can think of that looks close to 0, but is not identically 0 and is not continuous? So modify the function that's identically 0. What's the simplest way you can modify? When we played the Fibonacci game, I gave you one extra square. I did the smallest modification I needed to. If I just gave you one 1 by 1, 1 2 by 2, 1 3 by 3, 1 4 by 4, you weren't able to put down 2 squares. But the smallest addition of giving you a second 1 by 1 square, you were now able to form, spiraling rectangles that covered the plane. So if I take the function that's identically 0, that works. What's the smallest modification I can do to the function that's identically 0? And come up with something whose square is going to integrate to 0.
Smartass answer would be like 0.0001. That would work.
But is that 0.0001 everywhere? So what's the function? Tell me what the function is. It's probably going to be a split definition. What's the easiest way to modify the function that's 0 everywhere? I'm sorry? Okay, so give me a definition, give me a function that works. F of x is 0 here, and okay, so try f of x equals 1 if x equals 1 and 0 otherwise. That's the smallest change I can make and still have it work. Now, if I look at this, will the integral of f squared be 0? Now, I've got a function that's 0 everywhere but at one point. Changing it to being 1 at one point, is that going to affect the integral? No. So this will still integrate to 1. Now, this is supposed to integrate to 0 for any choice of g. This is now doing it for specific choice of g. We have to show that no matter what g we put in, this is still going to integrate to 0. Will this still work for any g? Yeah, I have a function that's 0 everywhere but one point. So no matter what g I put in, is it going to be fine? It should work, right? So, whoops. This works for all g. More generally, I could take f of x equals n if x equals n, which is an integer, and 0 otherwise. So here's a function that will have infinitely many discontinuities, but the discontinuities are well separated. So the idea is to try to get a sense of what kind of conditions you need. As a nice exercise, so let's reconsider. You go from -infinity to infinity, f of x, g of x equals 0 for all continuous g of x, and f of x is continuous. Anybody want to make a conjecture? One of them has to be 0. And so we're saying that the integral of f against any continuous g is equal to 0. So which one of them do you want to say has to be 0? This conjecture is f of x is identically 0. So as a nice exercise, try to write this up well. How would you write this up cleanly? How would you show that f of x has to be identically 0 if this is true for every continuous g? Has anybody here taken real measure theory? Okay, so in measure theory, there's a whole industry where you first prove things for continuous functions, then you prove things for functions that can be approximated by continuous functions, then you prove things for things that can be approximated by, and so on and so on and so on. And so you try to understand what's going on in simple cases. And so sometimes when you have a difficult problem, it's easier to first step back and say, well, what can I do in a special case? What if I go back and I now assume I can't use every G, I can only use G that are continuous? Or maybe I want to try to explore what's going on in the special case when F is continuous. All right. So now I want to talk about some integrations. So consider the following. Fn of x is continuous, non-negative. The limit as n goes to infinity of Fn of x equals 0. Okay. So I have a sequence of functions. They're non-negative, they're continuous, and at every point, the limit of Fn of x equals 0. If I integrate from, let's say, 0 to infinity of Fn of x dx, and I take the limit as n goes to infinity, that's one way of doing things. I could integrate for fixed n and then take the limit as n goes to infinity. What's the other way I could do things? So here, I first fix an n, I find the integral, and then I let n go to infinity and see what does this go to. What's the other way I could do things? Okay, so what should I write down? So here I took the limit as n goes to infinity of the integral. What could I do the other way? Well, I mean, that's basically what I'm doing right now. For each n, I'm taking the integral.
Oh, gotcha.
Right? And then I'm letting n go to infinity. So I'm integrating first, and then I'm taking the limit. What's the other way to do things? Then take the limit integrate. First is, take the limit as n goes to infinity of Fn of x, and then integrate from 0 to infinity. And I'll put in a bracket over here to just highlight the fact that in this case, I'm taking the integral first, and then I'm taking the limit. Or in the other case, I'm taking the limit first. One of these I think is very easy to evaluate. Which one do you think is easy to evaluate? The left-hand side or the right-hand side? The right-hand side. So what does the right-hand side equal? That's just 0. So do you think the left-hand side is always going to be 0? So should it matter which order I do things? Should the integral of the limit be the limit of the integral?
It does matter
Okay.
because you only know that the integral, you only know the Fn of x close to 0 for a large n, but for like a smaller n, it might not be.
Well, but I only care about what's happening as n gets large on the left-hand side. So for small n, anything could happen. If I wanted to, I could actually look at n starting at 2 billion or 15 quadrillion, doesn't matter. So when you take a limit, you can throw away finitely many terms in the beginning and it's not going to change anything. So I have a sequence of functions that are converging pointwise to 0. Does that force the integral to converge to 0? So in mathematics, you should learn that there are certain operations that are dangerous, that we have to be either careful with or we're not allowed to do. What is something you are not allowed to do as a mathematician? You're not allowed to divide by 0. You can divide by something that's approximately 0, but you are not allowed to divide by 0. If you look back to what's the definition of the derivative, it's the limit as h goes to 0 of f of x plus h minus f of x, that's the numerator, divided by h, which is the denominator. H is not allowed to be 0 in the limit. It's the limit as h goes to 0, but it's never 0. It's approaching 0. So we never divide by 0. Another thing that's extremely dangerous in mathematics is infinities. Whenever there's an infinity at play, you have to be careful. Where is the infinity at play, or where are the infinities at play here? So one is we have n going to infinity. That's one infinity. What else?
Integration.
The integration. So there could be two issues here with infinity. One is that we have the limit as n goes to infinity, so we have to be careful about that. The second is we're not doing this on a finite interval. We're doing this on an infinite interval, so things could be poorly behaved. So is it different if we have the limit as n goes to infinity of the integral, let's say from 0 to 1, fn of x dx, versus the integral from 0 to 1 of the limit as n goes to infinity, fn of x dx. Do you think one of these is more likely to be equal than the other? Or at least, is there one that is at least as likely as the other to be true, to have an equality? They might both be true, they might both be false. Does one of them seem more likely to be an equality?
My first inclination is the infinities because you smooth over any full.
So which one do you think is more likely to be an equality? The top one or the bottom? Which, so you think the top is more likely to be true? That, okay, because you have a infinity at play, things can be smoothed out. Okay. And so how's the smoothing happening?
Careful, I was gonna say you're taking it over a larger set of numbers.
Right.
I feel like it might be the bottom one.
Okay.
If you integrate from 0 to infinity, that also includes 0 to, so it's like a small.
Okay, so maybe, yeah, the second one I can extend to the first one by just saying, you know, my function is identically 0 from 1 onward, so that maybe the second one is a special case of the first. So I would be shocked maybe if maybe the first one failed and the second one was true. That would seem surprising, because I can always just restrict my function. So this is always a good insight. So the question is, if we think maybe the second one is more likely to be true, the bottom is more likely to be true than the top, can I come up with a function that converges to 0, but maybe it has some issues in terms of how it converges to 0? What this is just saying is that at every point, if you wait long enough, the function is going to get closer and closer to 0. In the limit for any point, it's going to go to 0. I'm not saying it goes to 0 at the same rate at every point. Is there anybody here who has not seen epsilons and deltas in a say calculus class or a real analysis class? You know, to show a function is continuous, this is the epsilon delta game. I will be on offense, and I'm going to give an epsilon greater than 0. And then once I give you an epsilon greater than 0, you have to give me a delta, so that if you are sufficiently close, if you're within delta of the point we care about, then the values of the functions are within epsilon. And if I give you a smaller epsilon, you can probably find a smaller delta that works. And no matter what epsilon I give, you can always find a delta. But if we look at different points, if I want to show the function is continuous at 5 or 17 or 24, 6 or 1, depending on which point I'm looking at, I might get very different deltas. So typically delta is going to depend not just on epsilon, but on the point you're looking at. So when I say the function converges to 0, I'm not saying anything about how it converges to 0. This convergence could depend on the point x. And so you might get to 0 faster at some points than others. And so can anybody come up with a function that might violate this, that might not have this equality. So can somebody give me a nice function that integrates to 1? Nice continuous function that integrates to 1. Yep, or from 0 to infinity. So let's take a function that integrates to 1, because we're trying to show that maybe the first thing is not correct. So one way to show the first thing is not correct is, what if I can find a sequence of functions that integrate to 1? Well, then what would the limit be? If for each n I get 1, then the limit would have to be 1. So if I can find a sequence of functions that integrate to 1, and the functions are pointwise converging to 0, then I'll be in great shape. So can somebody give me a continuous function that integrates to 1? F of x equals 0? What's the function f of x equals? If I give you the function f of x equals 0, its integral is just 0. I want a function that integrates to 1. So you're here is the real line. You're here's 0, here's 1, here's 2, here's 3. Give me a function such that the area under the curve is equal to 1. You should be able to give me a simple function. Which shapes do you know where you can find areas under curves easily? Squares. Okay, but a square is not going to be continuous. So let's go to a triangle. So give me a triangle that has area 1. From 0 to? Okay. So if I go from 0 to 2, the area of that is going to be 1. Wait a minute, no, that's going to be 2. It's going to be 2. Remember, it's going to be continuous. So I want a triangle whose area is 1, and then it's got to be 0 everywhere else. So what should the triangle look like? Just going all the way off to infinity? Because remember, you go up. Okay, well, so we go from 0 to 1. And then what do we do once we get to 1? Well, but it's not going to be continuous then. It's good. I'm sorry? But then it's not going to be continuous. It's going to have a jump discontinuity. Yeah. So what should I do? Once I go all the way up at 1, what should I do now? How high should I come up? Well, we started at 0. We go up to some point here. The function is going to be 0 from some point onward. Do we all agree on that? Where do you want it to start being 0? There we go. You'll come down like this. And so if we do it like this, now what's the area under the curve going to be? 1. So this is going to be, height 1. And so this has area 1. So let's let f1 of x be, I'm just going to write, I should be able to do this. 1 minus absolute value of x plus 1, 0 less than equal to x less than equal to 2, 0 otherwise. I think this works. So when x equals 1, this equals 1. when x equals 0 or 2, oh, it's okay. I want a negative sign here. There we go. I'll just write it a little bit better. One minus the absolute value of 1 minus x. This is just, the correct way to write down what is the triangle function. So if I choose that to be my function f1 of x, that's going to have area under its curve of 1. What should I take f2 of x to be? Do you have a thought?
Is our goal still to have the integral be 1?
We want the integral to be 1 every single time, and we want the limit as n goes to infinity of the function to be 0 at every point. So if I take so I could take wider and wider triangles. Okay, so that's one approach. So one possibility is maybe f2 of x is the following. So here's 0, 1, 2, 3, 4, ... So how wide would you want it to be now? Right, but I want a nice sequence so I can understand what's going on and I can write it down without too much trouble. I'm the one at the board in the generalized notion of what a board means in the 21st century. 0 to 4. I love 0 to 4. I think that's a great idea. And so if I go from 0 to 4, what's the height? A half. Let's see. The base is 4, so it's 1/2 base times height. So I think we want the height to be 1/2. And so if we take 1/2, we get area as 1. And so we would get f2 of x. So the key point, it's now going to be 2 minus absolute value of x. Right? And if we do 2 minus this, then when x is equal to 0, we'll have the maximum value. And when x is either 0 or 4, we would get 0. And so we have to then multiply this whole thing by, just 1/2. And this will be 0 less than equal to x less than equal to 4, and 0 otherwise. Will this still have integral 1? Yes. As you do more and more of this, what's going to happen in the limit? It's going to accrue to 0. So this will actually give us a sequence of functions that work. This is not the sequence I had. There's more than one way to solve something like this. This is a great example. What is essential for this example? With this example, could you use this for the one on the bottom, for the blue one over here, where we're integrating from 0 to 1? No, so this is fundamentally using the fact that we're integrating from 0 to infinity that we can escape out. So right now, you've done enough to disprove the first. The first cannot always be true. You've given me a sequence of functions. As a nice exercise, you want to then make this explicit. And, what would f sub n be? Anybody want to guess what f sub n might be?
1 over n times n minus absolute value of n minus x, and then 0 otherwise. From 0 plus equal to x plus n to 2n.
Yep. It doesn't want to let me do 2n. So that would work. So if we do this function will be pointwise 0, and we have the limit as n goes to infinity of fn of x is 0. And now we have a sequence of continuous functions. So this is one way to show that we cannot switch the order of operations. The example I was thinking of, It didn't actually copy the x-axis, it copied everything around it, but did not copy the x-axis. Fascinating. All right, so here is our function. Its integral was 1. Just shift it down. So for the next one, there's 0, 1, 2, 3, 4, 1. All we have to do is just shift it over. And then have it 0 everywhere else. And so basically, you have a blip that's traveling down. And so in both of these cases, it is absolutely fundamental that we have an infinite space to play with. If we had a finite space to play with, things would be false. So in terms of writing this up for a book, the question is, what's the best way to explain this? What's the best way to give people a chance to play with things and come up with stuff like this, to come up with these counterexamples? Are there other types of counterexamples you can have? Or is it essential that we have a infinity at play? So we already know enough that there's no way the limit of the integral is always the integral of the limit, even if the function is continuous, even if the function is converging pointwise to 0. So we're going to need stronger conditions. And this is how things happen in practice. People are interested in something, and so they start exploring and they start to see, what do I need to assume in order to get what I want? So we know the first, cannot be true. But what about the blue? Is it possible that if we restrict ourselves to integrating from 0 to 1, is it possible that this is true? What are your thoughts? Do our counterexamples apply at all here? Right. Right. Well, so both methods, the method you came up with, you had an ever fattening triangle. So it got very fat, but very short. But it needed that infinite space to work. The sequence I came up with is I kept all of my triangles the same size, but I kept shifting them over. So if I can't get past 1, I can't have translated triangles, and I can't have ever fattening triangles. So the counterexamples we came up with are completely unavailable if we restrict ourselves to 0, 1. So we would need something new in this case. And so we want the limit as n goes to infinity of the integral from 0 to 1, fn of x dx versus the integral from 0 to 1 of the limit as n goes to infinity f of x dx with fn continuous and the limit as n goes to infinity of fn of x equals 0. So I want something, I can't have things escaping past 1. Yes. So what if we make the triangle taller? I like this idea. So 0. So basically it's, look, you made them fat and short. So rather than making them fat and short, make them tall and thin. So where do you want to have your first triangle centered? So your first triangle, and where's your next triangle going to be centered? Okay, so the first triangle is centered at 1/2. And where do you want to go? From where to where? So 0 to 1, okay? So we'll start off like this. And we've got to go up to a height of 2. Right? Okay, so this is going to be f1 of x. Why can't we have f2 of x centered at 1/2? Well, we don't have to have it going from 0 to 1. We could have it go maybe from 1/4 to 3/4.
Because you couldn't do that. But you could actually pick this line.
What's the issue? What would it violate if every triangle was centered at 1/2 as it gets taller and taller and taller? What are we assuming is true about our function? Well, we're trying to make something integrate to 1. We definitely want it to integrate to 1, and we want our functions to be continuous, and we want it to be converging pointwise to 0. So what would happen if we always had our taller and taller triangle centered at 1/2?
Stop being.
Well, let's see what would happen. So here's 1/2, here's 0, here's 1. And let's say I'm looking at now maybe the nth triangle. I could do something like this. And maybe I'll choose it to have height n. And maybe this is 1/2 minus 1 over n. And this is 1/2 plus 1 over n. So the base is going to be 2 over n. The height is n, so the area is going to be 1. What's the problem with that if that's my next function? So I want a function to be continuous, and I want it to converge to 0 at every point. Well, what's wrong with the 1 over n? Well, I mean, n is just going to be the various integers. It'll be 1, 2, 3, 4. So is that triangle function continuous? Looks continuous to me. What's the other condition? Well, this is clearly non-negative. But, so the limit is supposed to be 0 at every point. If I take this to be my nth function, is it converging to 0 at every point? Where does it not converge to 0? I'm sorry? Well, you have to give me an x where the limit is n goes to infinity of fn of x is not 0. One-half. So the limit as n goes to infinity of fn of 1/2 equals infinity, which is not 0. So the problem is, if we tried to make all of the triangles centered at 1/2, that would be a problem. But you did not say that, right? Where did you have your second triangle centered? And where would your next one be? So one possibility is to do powers of 2. The other possibility is to do 1 over n. And so if instead we did something like this, here's 0, here's 1, and here is maybe 1 over n. And here's 2 over n. This is good. So let's call this our function fn. What's the area now? So what will the area be now? 1. And so now we will get that the integral from 0 to 1 of the limit as n goes to infinity of fn of x dx equals 0. And the reason is, you give me any value of x, either the value of x is 0, and the function is 0 for every value of n. For every n, fn of 0 is 0. And if x is not 0, then eventually n is so large that 2 over n is less than x. So either x equals 0 and fn of 0 equals 0, or eventually 2 over n is less than x, so fn of x equals 0. So we know that this function will converge to 0 at each point. But what is the integral from 0 to 1 of fn of x dx? That's just 1. So this gives us an example where we have a sequence of continuous functions, but we can't interchange the order of integration. So in the first set of examples, the difficulty was that we could escape to infinity. And we saw two different ways that escaping to infinity could cause problems. One possibility was the function could become extremely fat and spread out, but with small and small and smaller height. And the other one was we could just keep translating. And so we then said, well, what if we restrict ourselves to 0, 1? You're trying to figure out what conditions do we need? Wouldn't it be nice not to have to worry about, do I integrate first and then take the limit, or do I take the limit and then do the integral? If you're doing a lot of things, how many people are taking statistics or have taken statistics? So you all know the central limit theorem, and you want that central limit theorem to kick in, and you want to be able to use that. So we want to be able to look at limits of processes, and it would be nice to know when do we have to be extremely careful about stuff like this. And so it's not enough for us to just restrict to an interval 0, 1 with continuous functions. We need another condition. So not enough to restrict to continuous functions on 0, 1 with the limit as n goes to infinity of fn of x equals 0. Need more, try each fn is, so can somebody give me another property that might work? What else could you throw on that might prevent us from constructing something like this? That's how we get conditions. You look for something which is going bad. And then, okay, what condition can I throw on so that this badness will not happen? The first two examples, well, the badness was coming from the fact that I could go off to infinity. So I now said, okay, let's restrict it to 0, 1. And when I do that, then that puts me in a much better shape. Those counterexamples are no longer in play. Well, we came up with a new counterexample. We got very tall triangles. What kind of assumption could you put on the function that might prevent me from having tall triangles like this? Fn of x is? Yes. So one possibility is differentiable. Differentiable is not going to work because I could easily smooth this out. I could do this into like an ellipse or something like that. Differentiable is a natural thing to try, but it's not going to work. I need something else. What can prevent you from getting very tall triangles? The function is bounded. We don't know if that will work, but it's at least enough to eliminate this counterexample. This is how we make progress, is we see what goes wrong, and then what condition do I need to put in so that your counterexample is no longer alive. And so if I put in boundedness, that will be it. All right, this is a good place to stop.